Alright, so let's move to reaction 2. In this reaction, this is our starting material, and you could see that there is a 4-membered ring inside. We are having 1, 2, 3, and 4. There is a 4-membered ring inside the 6-membered ring, and this is an alcohol. So using the same Wagner rearrangement, there is something you are supposed to do to get a product that looks different. Because 4-membered ring and 5-membered ring, something can be done about it to expand this ring. So here we are going to move to the most stable carbocation and also consider the ring strain as a factor. So in the presence of HCl, let me try and redraw it again. Usually I tend to redraw it so that it makes everything simple, including the bonds. So you have the methyl group here, right? So the first thing I will do is to ignore the ring first, ignore the intramolecular ring, and just go by my O and H. And you know, in the presence of H2SO4, right, or in the presence of HCl, you should have something. So if I'm using HCl, then this lone pairs here, we are attacking this, and now I'll be having this. You get it? So from here, I'm going to have cyclohexane, alright. But this time around, to be in the form of water. So OH2 plus. And here, let me try and indicate in the methyl groups so that it won't confuse. Sometimes when you see that you are getting confused, just try and indicate the methyl groups so that the lines will not confuse you, because you are using a dash formula. Some of the lines might confuse you, especially the number of atoms. So here, the next thing you're supposed to do is to allow the water to leave, because it is a good leaving group. And then you are going to have a carbocation. Where on this side you have your methyl group, so CH3, and on this side you have just a positive charge and a hydrogen. So this is a positive charge here. Now let me try and introduce my ring, because this is where I'm going to do a whole lot of stuff. Right, this is my 4-membered ring with the 2 methyl groups here. Okay, so now I'll come to the bottom, right, and now I will do something like having my secondary carbocation. Something can be done about it, right? I'm having a secondary carbocation. Okay, so having my secondary carbocation, and I'm having a positive charge here. You get it? Here we need ring expansion. We can actually move this ring to this side, right? If not, we would have done a methyl shift. But because we can move this ring only to this side to expand it to the 5-membered ring form, then the only thing we can do is to actually make a migration point. We are going to move something from this side to this side so that to allow the positive charge to be here. So right now what we are going to do is that we are going to do a hydride shift, because first of all we want to move from a secondary to a tertiary. That is possible, and when we do that we can also use our opportunity to expand the ring. So there is a hydrogen here, right? Now we are going to move this hydrogen onto the carbocation. So the same thing that you are seeing here, now we are having our hydrogen here, and now we are having our methyl group CH3 with our positive charge here. And now let me introduce the 4-membered ring. You are having this. You are having the methyl groups. You get it. So you see how it's very nice and interesting doing it. Let's try and see the last thing we can do. And the last thing we can do, let me try and move backwards, because I can merge the reaction there. Right, now I can move this particular ring all the way to this side, to where the carbocation is, and see it is 1, 2, 3, and this is 4. Now let me name this one as, let's say, an asterisk. You could see that I'm moving this ring, which is the ring 3. I'm moving it all the way to this side. So this is the ring 3. The bond between carbon 4 and carbon 3 is going to move, and I'm going to move the third end, right? Where the carbon 3 is, that's the bond I'm breaking and putting it on this particular carbon named the asterisk. For that matter, I'm going to have my cyclohexene. Let me try and draw it big. Okay, so that everything that we are doing will fit in. With this, I'm going to have my CH3 also here. And now see, I'm going to have my compound, alright. But this time around, it's not to this carbon. The bond is from carbon 4 to carbon 5. And our methyl groups will still be here, right? And now what do you think? Because the bond was here, right, and we've broken the bond as carbon 3 and placed it on the asterisk carbon, right, then this means that carbon 3 will be having the positive charge. Okay, so with our positive charge, remember we use HCl, right? So our Cl minus will come inside because we are using aqueous, we are not using a dehydrating agent. So now our Cl minus will come in to where the carbocation is, and now we are going to have this, and this to this to this. Now you're having our 5-membered ring inside. This 5-membered ring is here with our 1, 2, and then we are having our methyl group here, CH3, and then of course we are having our Cl. So you see, molecular rearrangements. We never expected that this product will be converted to this product. Okay, so this is the most interesting part of whatever that we are doing. We never expected it. You remove your OH by protonation, it goes as a good living group, and then you are going to have your rearrangement in terms of stable carbocation where you do a hydride shift. So here there is a hydride shift. This first is one of our first rearrangement. So hydride shift first, then we move on to the ring expansion. And from the ring expansion, we did the nucleophilic attack to just have our compound back, and this is our rearranged molecule, or the major product. So this one is the Wagner rearrangement. Now let's try and move to cyclohexene, but this time we are not going to draw it this way, we are going to draw it in another form. So this kind of cyclohexene, that will be reaction 3, right? So reaction 3 will be in soon, so just watch out for reaction 3. But this reaction is very easy and it is simple. You have to understand the concept. If you're having 5-membered ring, you're having a 4-membered ring inside a 6-membered ring, if there's a possibility that you can actually expand this 4-membered ring even to 5-membered ring, yes. If you can do it, if it is 5-membered ring and you can expand it to 6-membered ring, yes, do it, because we want to achieve stability, the most stable product. And Wagner rearrangement, the driving force, it is being driven by most stable carbocation as well as the most stable compound with a less ring strain. So that brings us to the end of reaction 2. Now let's move on to reaction 3.